Hello everyone, my name is Ismail and I'll be talking about BGP routing policies in ISP networks in this presentation. Here is a brief outline of the points we will cover in this presentation. We will first start by introducing BGP and describing what it is and how it works. We will then talk about how the route selection process is done in an ISP and highlight some of the issues faced by BGP. Then we will go over the common design patterns ISPs have adopted in their BGP routing policy. We will finish off the presentation with possible improvements to alleviate the problems of BGP. Before I introduce BGP, it is important to know what autonomous systems are. An autonomous system is a large network or a group of networks that has a unified routing policy. A few examples of an AS are a network service provider, a large company, or a group of companies or a university. Today, there are over 100,000 autonomous systems in the routing network of the Internet. So, having defined an AS, we can now introduce the Border Gateway Protocol, or BGP. BGP is a dynamic routing protocol that decides the route based on path length, configured rules, and most importantly, network policies. BGP enables the Internet to exchange routing information between autonomous systems. In other words, inspired from the CS438 lectures, BGP is the routing protocol used to exchange reachability information across ASs. This reachability information is also called an advertisement that can be propagated to neighboring ASs, called peers. The neighboring ASs communicate through the border routers of an AS called eBGP peers. Whereas the internal routers of an AS are IBGP peers, the main difference between the two is in the propagation, where eBGP advertises learned routes to IBGP and eBGP peers, whereas learned routes by IBGP are only propagated to eBGP peers. The need for this complex routing protocol arises from the demand to decide routing paths and which routes to propagate to neighbors. Due to this demand, ASs, specifically ISPs, started to alter routing configurations to reinforce routing policies. What makes this protocol special is also what makes it complex. The complexity arises from trying to understand the routing decisions that makes this protocol special. To best understand this protocol, we take a look into design patterns commonly used in routing policies used by ISPs. So, the policies ISPs define are implemented when processing advertisements. Advertisements in BGP are processed in 3 steps. First, the ISP enforces an import policy to determine the unstable routes and filter them out of the decision process. Second, the router undergoes a decision process to determine the most suitable route. Finally, the export policy determines the neighbors that the suitable route will be exported to. In this slide, we will touch on the BGP decision process and the basis on which it was developed. To give operators greater control over route selection, attributes were added to advertisements. These attributes create criteria based on which routes can be compared. The route descriptions given by attributes result in the decision process. The included diagrams show example decision processes of ASs dealing with BGP. In the table below, we can see how different attributes are listed. The steps represent the priority from highest to lowest, where advertisements with similar local pref values will check for lowest path length, and so on. The third column simply describes the location where the corresponding attribute was configured, either locally, externally, through neighbor, or static attributes that are set by the protocol and cannot be changed. Given what we know about BGP routing, it is clear that there is room for flaws. The purely trust-based peering design causes major concerns in terms of security, ranging from attacks on message integrity, even to attacks between peers. Given the constant change in policy, BGP is also prone to errors due to misconfigurations and conflicts between policies at different ASs. The decision process is complex because the demands from ISPs are always changing. To better understand these changes, we'll skim over some of the most important policies used in ISP routing decisions. Generally, ISPs select routes that adhere to their relationship and agreements with neighbors. The three relationships we will look into are customer-provider, peer-peer, and backup relationships. In the customer-provider relationship, one ISP pays the other to forward its traffic. In the peer-to-peer relationship, two ISPs have a mutual agreement to directly connect to each other without exchanging payment. This could possibly be because of equal amounts of traffic they have. Finally, in the backup relationship, two ISPs can set up a connection that is only used when a failure occurs at either side. These three relationships play an important role in routing policy. Given that most ISPs have a customer-provider relationship with another AS, ISPs have a higher tendency towards customer-learned routes because of revenue generation. On the other hand, sending traffic through providers will cost the ISP money. In the case that one ISP sends traffic to a peer, this traffic may skew the traffic flow, which may ruin a peer-to-peer relationship. ISPs can configure a range of values for the local pref attribute where a local pref creates a preference depending on these relationships. Attributes such as local pref can also be used to control traffic to reduce cost. As an example, an ISP in the US can specify a lower local pref value to avoid directing traffic through an expensive link to a country in Asia. Another attribute useful to the business aspect of BGP is the community attribute. Routes learned from peers are tagged with a community attribute which an ISP uses to filter out these routes. Thus, the community attribute gives an ISP the control to determine which routes to and not to export. To understand the concept of customer-provider relationship, let us have a look at the example in the graph below. Suppose that A, B, C, and D are provider networks and X is a customer network. Now, suppose that A advertises to B path AX and B advertises to D the path BAX. B should not advertise to C the path BAX because C is not B's customer and would not benefit B in this case. Sometimes ISPs have several links to their neighbors to reduce delay and improve reliability. Another goal for ISPs is to meet certain performance criteria. This is done by modifying the import policies of its routes. This is done by modifying the import policies of its routers. This will ultimately give ISPs the ability to reduce congestion on outbound links to neighbors and shift traffic between links to different neighbors. To begin with, let's look into outbound traffic control. The outbound traffic can be controlled either by configuring import policies or by modifying IGP link costs. The first goal is to reduce internal congestion. This is done by using early exit routing or hot potato routing. It can also reduce traffic internally, as this protocol forwards traffic to the closest exit point possible. As a result, the number of links packets traversed is reduced and hence the corresponding congestion. The second goal is to reduce traffic on links to neighboring ISPs. The process of shifting traffic from a neighboring ISP to another is called load balancing. This is done by changing the values of the local pref attribute. To give you a better understanding of how this works, let us take a look at the figure. For example, let's suppose that the links between B and A are overutilized or that the links will be taken down for maintenance. B will shift its traffic to C by increasing the local pref for routes traversing through C and reducing the local pref for routes traversing through A. Next, we will go over inbound traffic control. Inbound traffic control is responsible for controlling the traffic received from other ISPs over a specific link. The reason why an ISP might want to control the traffic received is to ensure that internal congestion is not worsened. Inbound traffic control can be done by manipulating the route attributes such as the MED attribute or by AS prepending. Obviously, it is difficult to control the traffic being sent from neighboring ASs as they are independent in the decision making. However, Due to the nature of BGP, ISPs connected with multiple links can come to an agreement where increasing a router's MED attribute value can make that router less preferred, thus lowering the load on that router. As shown in the diagram, AS A and AS B are connected through links at R1 and R2. If B wanted to reduce the incoming traffic to R1, then it could increase the MED attribute R1 advertises to A. This in turn will cause A to prefer sending traffic through R2 and thus reducing the traffic to R1. AS perpending, on the other hand, involves creating an illusion of a longer AS path length. This is done when an AS adds multiple copies of its AS number to the AS path, thus artificially inflating the AS path length. As an example, B can artificially inflate the path length of routes to A, thus causing routes to C to be more preferred. In this slide, we'll cover the scalability policies that are important for stability in ISP routes. Malfunctioning routers and ISP misconfigurations can generate excessive update rates. This results in extreme overload in routers' processing and memory capacity, causing failures, outages, and unstable routes. To prevent such router failures, ISPs use methods such as limiting routing table sizes and limiting the number of routing changes. Limiting table sizes can be done by filtering long prefixes in advertisements from neighbors, limiting the number of prefixes that a neighbor can advertise, or just employing default routing. Default routing simply means that an ISP sets a default forwarding route for destinations not on the routing table. The second method of dealing with route instability is a procedure known as flap damping. Flap damping basically marks a route as ineligible for use as an active or preferred route. This is done by associating a penalty value with every update where the route is marked as unstable. The penalty value exceeds a certain threshold. Next, we have some security policies that try to avoid and deal with malicious attacks and false information in the network. First, ISPs enforce import filtering policies to discard invalid routes. The ISPs perform checks to ensure updates are valid before propagating them internally. As an example, advertisements from customers for prefixes they do not own should not be propagated. Moreover, a Tier 1 ISP should not accept any routes from its customers that contain another Tier 1 ISP in the AS path. Second, ISPs delete or rewrite attributes to protect integrity of routing policies. This prevents peers from violating peering agreements by wrongly configuring attributes to certain IP addresses. The same can be done for other attributes, yet this does not prevent all violations of peering agreements. Third, ISPs need to block denial of service attacks. Denial of service attacks are basically intended to shut down a network. They can overload routers with an extreme number of update messages with the intent of causing a failure due to overload. One way to prevent this is by setting a cap on the number of acceptable prefixes. In the case that the limit is exceeded, the session will be teared down. Now, due to the complexity and unpredictability of BGP, several research has been done to solve the problems BGP faces. Tools have been developed that can aid in detecting, testing, and debugging BGP configurations before deploying them in networks. Moreover, today's advancements provide solutions to the limitations on network performance factors. One solution is BGP NCM that utilizes monitoring, traffic calculation, and configuration modules to optimize link utilization. Thank you. This was the end of the presentation.